Before we focus on the ground state and first excited state of the hydrogen atom, I want to review with you the quantum numbers that we got and the range of each of these quantum numbers. There are three quantum numbers that we got. We first got M, the next one we got was L, and the last one we got was the principal one, N. Okay, we use the letter M for the first quantum number. The textbook called it M sub L. It's the same thing. Okay, it's the same thing. It's a little cumbersome. I didn't write down M sub L. Just call it M. There are names associated with each of them. I only told you one name here, the principal quantum number. Principal means it's the most important one having to do with energy. The L and ML also have their own names because of their physical meaning. I have not discussed that in detail yet. L is called the orbital quantum number, and ML is called orbital magnetic quantum number. The names will make sense if we discuss what they represent later. Okay, so that will come later. What I want to talk about again is the range of these quantum numbers. N, the principal quantum number, is a natural number. 1, 2, 3, 4, 5, and so on. 1 meaning the lowest energy, the ground state. 2 meaning the first excited state, and so on. The energy of the system depends only on N. It has nothing to do with L and ML. Okay, so besides the ground state, the first and second, all these excited states of the hydrogen atom are degenerate. You know what that means, degenerate? Remember the last part of the previous chapter? Degenerate means you can have different quantum states corresponding to the same what? Same energy. Okay, so for n equal to 2, for example, L can be equal to 0 and 1 because L can go all the way to n minus 1. And ML, for each L, this M can also range. There is a range. So therefore, there are a bunch of states with different L and different M. But they have the same n, which is 2. And therefore, all these states are degenerate because they have different wave functions, yet they have the same energy for n equal to 2. Okay, so the only non-degenerate state for the hydrogen atom is the ground state, where n equals 1, L is equal to 0, and ML is also equal to 0. Apart from that, you're going to get degeneracy, and so we need to use some conventions to label these different states, or different N, different L, different ML. Now, for L equal to 0, we call it the S state. L equal to 1, we call it the P state. L equal to 2, we call it the D state, and equal to 3, we call it F state. Usually that's enough. These symbols, S, P, D, F, many of you are familiar with them from chemistry. These are symbols we use in spectroscopy when we study the light coming out of these atoms. So in spectroscopy, these are the symbols we use. So when you see a 1s state, what does that mean? This 1 here means n equal to 1. So it's the ground state with L equal to what? 0. That's the only possible L you can have for n equal to 1, because L can never exceed n minus 1. Okay? And what about 2s? 2s means n equal to 2 and L equal to what? To 0. What about 2p? 2p means what? Means n equal to 2, but p is L equal to 1. Okay? Do you have a 2f? Do you have a 2d? No, there's no 2d, because d means L equal to 2, and n being equal to 2, L can only go to 2 minus 1, which is 1. Cannot have L equal to 2. So there is no such thing as 2d. There is such a thing as 3d, and so on. And here I have a question. What is the total number of distinct L and M combinations for a given n? For example, if n equal to 10, okay, how many different combinations of L and M can we possibly have under this restriction? So basically, we're just adding, first of all, for given L, we have this many values of ML, right, which is actually 2L plus 1, 2L plus 1. So 2L plus 1. That's the number of distinct states for given L. And then we have to add all the possible values of L. So L goes from 0 all the way to n minus 1. Right? This is the number of possible combinations of L and M for a given n, right? Because L goes from 0 to n minus 1. What is this equal to? This is not hard to do. It's just a algebraic series. And if you did that, you find the answer is very simple. It's n squared. N squared. For n equal to 1, n squared is still equal to 1. There is only one state, which is 1s. That's it. For n equal to 2, n squared equals 4. And there are four distinct combinations of L and M which will satisfy n equal to 2. And which are these four distinct states? Well, one is the 2s, okay? That is when L equal to 0 and M equal to 0. And the other three are all 2p's. For 2p, n equal to 2, p means L equal to 1, but there are three different values of m, -1, 0, and +1. So total number is 4. And for n equal to 3, there are 9 states corresponding to S, P, and D, and so on. And this is a general equation, general identity, which will come in handy when we deal with multi-electron atoms later. Now, with this out of the way, we are going to take a look at some of the low-lying energy states of the hydrogen atom, in particular the 1s and 2s, and we'll also take a little bit look at 2p as well. So let's start with the 1s. So for the 1s state, L equal to 0, for L equal to 0 S state, any S state, you can write down YLM. It does not depend on the angle phi. Okay, it does not depend on angle phi for any S state because M equals 0. But if L is also equal to 0, then we have the only YLM that has nothing to do with the angle theta either. That is the only isotropic distribution in space, as we saw before. Y00 is just a constant. Okay, so the 1s state is the only spherically symmetrical distribution of charge. And then what is the full wave function? The full wave function has three quantum numbers, n, L, and m, right? So it's 1, 0, 0. Okay? R10, that's the radial part, times Y00. Y0 again, it's just a constant. The R10, as we saw, is something like this, e to the negative alpha r. Alpha, in fact, is 1 over the Bohr radius. As we solve the Schrödinger's equation for r, that's what we got. And this thing has to be normalized, which means the chance of finding this electron under the state of 100 in every possible part of the space, if you add all together, should be 1, right? And so we integrate psi squared, okay, modulus squared, over the entire space. That should be 1. Now how do we integrate that? There is a c. You take that c squared out after you take the modulus squared. Here is the radial part. You have to take squared, so it's squared, so it's e to the negative 2 alpha r, and then r squared dr. The element, the volume element is r squared sine theta d theta d phi dr, right? So it's r squared here. And this r goes to from 0 to infinity. From 0 to infinity. That's the r equation. When you integrate over theta, theta goes from 0 to pi. There is a sine theta. When you integrate from phi, for phi, this goes from 0 to 2 pi. The entire integration should be equal to 1. You can easily work this out, work this out, work this out, and you find c must be equal to 1 over the square root of pi a naught to the power 3. That is your normalization constant. Now, the electron, how did we say it was behaving in the Bohr model in the ground state n equal to 0? Equal to 1. In a ground state, here's the electron, here's the proton, and here's the electron. The electron moves in a circular orbit, right, with a fixed distance, a naught, the first Bohr radius. I know for sure the electron is this far from the proton. The chance of finding this electron here and there, everywhere else except this orbital, was 0. And I said that was a naive picture. Because in reality, the electron can be found anywhere in space. Anywhere in space. It's a fuzzy picture instead of a very clear picture. And this calls for the idea of what's called electron cloud. The electron cloud really is just a rendering of the wave function using darker colors for higher density probability and lighter colors for lower density probability. So it's a visual idea of where can you find this electron more likely, where can you find the electron less likely. So you have a spherically symmetrical distribution of probability density. Therefore, the electron cloud should be spherically symmetrical, but it should be fuzzy, like a ball. And we'll see it in the next chapter. Okay, this replaces this very simple but naive picture of the electron moving in a circular orbit of given radius. What we want to know is the so-called radial probability density. Radial probability density, what is that? Suppose I look at a shell centered at the location of a proton between r and r plus dr with a thickness dr. And I want to ask myself, how likely can I find this electron to be within this shell? Well, that probability is called dp. I call it dp. dp would depend on two things. Depends on the probability density, which is the probability per unit volume of finding this electron there, and that's psi squared, right, by definition of psi. And the other is the volume of this shell, dv. So this is the probability per unit volume multiplied by the volume. Don't you get the total probability, right, dp? We call it dp because it's a very, very small probability, dr being very small. dv is 4 pi r squared dr, and therefore we can move that dr, only dr, over. I get the probability of finding the particle between r and r plus dr per unit length distance, okay? Per unit length distance, because it's dp over dr, and that is called radial probability density. That is the definition. And the textbook gave it a different symbol. We call it dp over dr. The textbook simply call it p. It's the same thing, okay? And what is that equal to? When we move the dr over, it's 4 pi r squared times psi squared. This is the so-called radial probability density. Again, is the probability of finding this particle a distance r from the nucleus per unit distance difference, per unit r difference. And with our definition, you can see for the ground state, 1s state, what is the radial probability density in the 1s state? We call it p of 1s. By definition, psi 100 squared, 4 pi r squared. You plug in psi 100, which is right here, CB in this, and this is what you got. Okay, it's something like r squared and e to the negative 2r over a naught. Now this r squared, where did that come from? It comes from here, which in turn come from the area of the spherical shell. So as you go out, on the one hand, the shell volume grows because the area grows like r squared. So that makes it easier for you to find the particle within that shell. But on the other hand, the probability density itself drops exponentially like that. Okay, so it's the product of these two. You are, as you go out, you're looking at a bigger and bigger volume, but with lighter and lighter probability density. So the total probability of per unit length is given by the product of these two. One function increases, the other function decreases, and as a result, you will see a total function which grows first and then dies down later. And that is what we see in this plot. This is a plot of the radial probability density for the 1s state. Again, it goes like r squared to the negative 2r over a naught. Goes up and goes down. What is the significance of this peak? This peak is at a certain location, certain distance, such that at this distance, the probability of finding this particle there per unit separation r is the greatest. In other words, this is the most likely distance that you will find this particle, find this electron. How do you find the location of this peak? Very easy. All you have to do is find the maximum of this function with respect to r. You can do that by setting what? Setting dp1s over dr to 0. Right? This is dp1s. Forget about constant in front of it. And if you did that, it's a very simple calculation. You did that, you find, believe it or not, you are getting a very familiar value, a naught, okay, which is this a naught here. The chance of finding this particle is the greatest when you're looking at one Bohr radius away from it. And that gives us a new interpretation of what the Bohr radius really means. According to the Bohr model, the particle can only be at one Bohr radius away if it's in the ground state. So the probability would be like this, would be 0 everywhere else, and it will peak to infinity. Okay, it will peak to infinity, and it goes back to 0. That was the naive Bohr model. The actual behavior is like this. The particle can be found here, 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 everywhere, except it's more likely to be found to be here. But it's not highly concentrated like this. It's not a delta function like this. So this is a better picture. It's a more realistic picture of what the electron really does in a 1s state. And here I have a computer rendering of the spherical distribution of the radial probability density. So it goes like this. This is lighter, and outside is also lighter. So as you go out, you find it's darker and darker because the chance of finding this particle increases, and it peaks at 1 Bohr radius, and it starts to go down and down and down. So this gives you some sort of visual idea. It's like a plot of electric field lines, that sort of thing. It gives you a visual idea of what the electron, where the electron can be found, and this is a picture of what's called electron cloud. Electron cloud. So this gives us again a new meaning of the Bohr radius. Here is, that was the 1s state. Now let's do some more calculation. Given this radial probability density, I can do a lot more calculation. I want to know more about this, the behavior of this particle. For example, I want to know what is the mean distance between the electron and the proton. Now the mean distance, if you follow the Bohr model, there is only one distance possible, which is A0, right? So the mean distance is equal to A0. But in our case, the particle can be found anywhere. So what is the mean distance? You know, this is not a symmetrical curve. It's got a longer tail here than there. So clearly, the mean distance should be somewhere away from that peak on this side, right? It should be somewhere here, right? So the mean distance should be somewhat greater than A0. Somewhat greater than A0. That's what we expect. And we also can find another thing, that is, how likely can the electron be found within the first Bohr radius? It's between here and there. You know, when you integrate over this radial probability density, you're going to get what? You get 1, right? Because the chance of finding this particle between r equal to 0 and r equal to infinity is 100%, right? So the chance of finding this particle anywhere between 0 and 1 Bohr radius would be just this area, isn't it? Is this area more or less than the total area, than half of the total area? Well, from this plot, you can easily see this area is somewhat less than the total area. The total area is that much, right? So again, in the next page, we're going to calculate two things. One is the mean distance between the electron and the proton. We expect to be somewhat greater than A0. And the second thing is the chance of finding this particle somewhere between 0 and A0. We expect it to be somewhat less than 50%. Let's see if that's the case. So I now set out to calculate the mean value of R in the 1s state and the chance P of finding the particle between 0 and first Bohr radius for this ground state 1 psi of 100 or 1s state. This is how I find the mean value of R. It is R times dp. What's dp? dp is the chance of this particle to be found between R and R plus dr. Okay? Times, so basically this is the weighted average of R. The weight is dp. And we have to sum over all the possible values of R, and then you get what your answer is. And it's basically it's R times ps dr. That's the definition of P1s. P1s is defined as dp over dr, as we saw before. And P1s is given here. We already found the expression. And all you have to do is to find this integral of r to the power 3 e to the negative something r dr. You did this calculation, you solve for this integral, you're going to get 3 over 2 a0. That's what we expected to be qualitatively true because we know it's somewhere outside a0, right? Somewhere outside a0. Just a little mathematical note. How would you find the integral of r to the power 3 e to the power something r dr? Easily. Many of you know that easily how to do that, then just forget about what I say. You already know how to do it. If you want some assistance, here is the answer. R to the power 3 e to the negative beta r dr going from 0 to infinity is 6 over beta to the power 4. You can try integrating by parts, but that's tedious. Okay, there is an easier way to do it. We call this I3. This integral we call it I3 because it's r to the third power. I'm going to start from I0 with no r to the power. That I0 is very simple. It's from 0 to infinity e to the negative beta r dr. That's just 1 over beta, right? Of course you know how to do that. And what I want to do is going from I0, I want to get I1, I2, and then I3, or any I for that matter. How do I bring an r down so that I can go from I0 to I1? You know, I can bring that r down by differentiating both sides with respect to what? To beta, right? If I did that, I would get negative r coming down. So I have a negative r, and this side, I differentiate with respect to beta, what do I get? Negative 1 over beta squared, right? Isn't that simple? That gives you r to the first power. And from here, that's I0, that's I1, right, already. How do you get I2 then? You want to bring another r down, so you do the same thing. Take one more derivative with respect to beta, you get r squared, and here just take one more derivative on this side, which is also very simple. So you did that, you're going to get easily this, r to the power 3. Okay? Otherwise, what if I want to calculate r to the power 10? If you differentiate by parts, integrate by parts, it's going to take you a lot of time. It's just a little side mathematical note. Anyhow, so we got that. That's one example for the average r, as we expect, somewhat greater than r naught. In fact, it's 1.5 r naught, a naught. Okay. Now let's calculate this probability. The chance of finding this electron to be within the first Bohr radius. So r is between 0 and the first Bohr radius, a naught. So we need to integrate dp, basically. dp is the chance of finding this particle between r and r plus dr. Okay? And so by definition, it's p of 1s dr. p1s is given by this, and you have to integrate between 0 and a naught. So here, this integral can also be easily worked out. There is a little trick, that is, we use what's called a new variable, dimensionless variable u. U is defined as r over a naught. R over a naught. So that makes, if you did that, you're gonna turn this integral into something like this. And in fact, there's got to be a 4 here, because there's a 4 here. So there's a 4. But anyhow, you can easily work this integral out. You can integrate by parts, or you can use the same trick that I did here. It doesn't matter, whatever you do. You're going to get this. This is the final answer. It's 32.3%, which means, roughly speaking, the chance of finding this particle to be within the first Bohr radius is about a third. There is about a 2/3 chance the particle is found outside the Bohr radius, about 1/3 to be found within the Bohr radius. So the electron spends about a third of the time inside the first Bohr radius, and here is the same plot for P1s. And again, this is the peak, that's the first Bohr radius. And if you look at the average or mean value, the mean value is somewhat on that side. That is, in fact, 2/3, a naught. And this area is about 1/3 of the total area, and that is to say, there is about a 1/3 chance the particle is found between here and there. The textbook calculated the probability going from here out, and it turned out to be 66.7%. Of course, that matches our answer as well. And now let's take a look at the next level, the first excited level, n equal to 2. And we have 2s or 2p. First, let's take a look at 2s. Okay, for 2s, you have psi nlm, n equal to 2, l equal to 1. I'm sorry, l equal to 0, that's s state, and m also equal to 0, so it's 2, 0, 0. And here is the radial part of the wave function. The radial part of the wave function. The b in s state, the angular part of the wave function, I didn't write it down because it's spherically symmetrical. Okay, s means l equal to 0, and m has no choice but to be 0 as well. So you have just a constant for the angular part of the wave function. I didn't bother to write it down. But the funny thing here, one funny thing immediately you notice is that there is a point where this psi goes to 0, and it's very clear it's 2a naught, right? 2 minus r over a naught equal to 0. So the wave function goes down to 0 at r equal to 2a naught. Now, isn't that weird? So here's a plot of the behavior of the electron cloud as a function of the angle, not a function of distance, a function of the angle. The 2p state has 3 possibilities of m. For m equal to 0, you look at this, it's a cosine function. The cosine angle is defined to be the angle between the vector r and the z-axis, and so that's the cosine angle. Being equal to cosine squared, which means I start from theta equal to 0 and go down, the wave function should get less and less and less. Cosine theta equals 1 here for theta equal to 0, and gradually diminishes when it goes to 90 degrees. When theta goes 90 degrees, cosine theta equals 0, you got nothing. So therefore, the wave function diminishes, you see here, as I increase theta from 0 to 90 degrees. And it's, of course, symmetrical here as well. This is when theta equals pi, cosine squared pi, again, equals 1. So it behaves like this. Okay, this is how it depends on the angles. And I have a plot like this. Now, this plot incorporates both the information on the angle and information on the distance r. So the further away you go out, the more diminished the probability is. So it depends on the distance r as well. But these three plots gives you more of an idea how it depends on the angles. And these two, I'm looking at m equals plus or minus 1, so therefore it's a sine function. So you see it actually is 0 at 0 degrees and maximum at 90 degrees. So you just take this guy and turn it 90 degrees, so it look like this. Look at something like this. Okay, so these are the some schematic plot of the electron cloud behavior for the two p states, and you can see here it's very different from our naive picture of circular orbital with fixed distance. And again, we have in this lecture we established the Schrödinger's equation in spherical coordinate, and we solved the Schrödinger's equation when u is a function of distance r only. We separated the variable, the angular variable, from the radial variable. The angular variable will yield a universal solution for any spherically symmetrical potential, and that is the spherical harmonics, YLM. The radial part depends on the wave it depends on the specific potential, and for the Coulomb potential, we got this solution which, according to the quantization condition, will give us the energy as the same as the Bohr model, except here the quantization condition is naturally obtained by satisfying the boundary condition at theta equal to at r equal to infinity, and then we arrive at the better description of the behavior of the electron. So we use the electron cloud to replace the fixed radius orbitals. So we recovered the same expression for the energy that was successful in the Bohr model. It continues to be successful, but the actual picture of the electron moving has been drastically modified. So make sure you correct your view if you think of the electron as just moving in circular orbitals. In fact, the more you study in quantum mechanics, the fuzzier the picture looks like. And this is a reflection of the quantum nature of the microscopic world, using a wave function to describe the probability only, not the exact whereabout of this electron. We have not studied the physical meaning of the quantum numbers L and M just yet. This again has to do with angular momentum. So we will look at the meaning of L and M, look at the angular momentum and the conservation of angular momentum in a spherically symmetrical potential. And we'll do that in the next chapter. Next lecture. We're also going to look at what's called a fine structure, and that is the energy levels. Most of these energy levels, turns out experimentally, if you take a really, really good look using a good spectrometer, you find that these energy levels are not single levels. Each one, most of them at least, is actually split into two closely spaced levels. The energies are slightly different between these two closely spaced levels. Why is that? Can we calculate the splitting between these two very close levels? This is called a fine structure, and we'll see the physics behind these fine structures and see how we can calculate that. So our study of the atomic world using the Schrödinger's equation is just beginning.